Before diving into the world of audio in the digital domain, we need to understand the fundamentals of audio. And the simplest way to talk about a subject is to figure out the elemental parts that make up the subject. For a lot of areas of study, this is fairly hard to do, since the makeup is ambiguous and fairly hard to single out. But in the world of audio, it's unmistakably simple. Simple harmonic motion. The physics behind sound and the generation of simple harmonic motion is described in another module on acoustics, but let's talk instead about the mathematics behind simple harmonic motion, and more specifically, the sine wave. We've all seen the sine wave before, the squiggly, wavy shape that you see in music equalizers. A sine wave is the purest form of audio, which represents an exact frequency or a tonal value. In fact, sine waves don't exist in isolation in nature. No natural source of sound generates a singular sine wave, but rather a multitude of sine waves bundled and added together. More surprisingly, it's possible to recreate any sound, including the sound of my own voice, by just adding different sine waves together. Although this can get expensive and absurdly complicated, and there are different synthesis methods to recreate more complex sounds, which you will be learning about later on. Sine waves can truly be thought of as building blocks of audio, like pieces of Lego. Since sine waves are quite essential to the study of audio, and since digital systems can produce single sine waves, we need to get a good grasp of where the sine wave originates from. And we go back to the humble beginnings of the triangle, and more specifically, the right-angle triangle. We choose the right-angle triangle here since it has a few established properties that we can leverage. So what do we know about the right-angle triangle, apart from the fact that one of its sides is at a 90-degree angle with one of the other? We know that since the sum of all the angles of a triangle is 180 degrees, the sum of the two other angles of the triangle has to be equal to 90 degrees. Here, angle A plus angle B equal to 90. We also know that the Pythagorean theorem is established for right-angle triangles, where it states that the sum of the squares of the sides of a triangle is equal to the square of the hypotenuse. Written out, it's simply x squared plus y squared equal to hypotenuse square. What else do we know? We know that there are certain well-defined but arbitrary ratios that are conjured up for the right-angle triangle. These ratios provide relationships between the sides and angles of a right-angle triangle, and they're called trigonometric ratios or trigonometric functions. There are 6 in all, but 3 of them are more commonly used. That's the sine of an angle A, which is the ratio of the opposite side to the hypotenuse, the cosine function, which is the ratio of the adjacent side to the hypotenuse, and then we have the tangent function, which is the ratio of the opposite side to the adjacent side. You might have noticed that the sine function is already described here. The end goal of the module is to describe the sine function, but it's not yet in a form that's recognizable or consumable for audio purposes. So let's push on. You might wonder at this point of time what the purpose of these trigonometric ratios are. They are just made up fractions, after all, that describe some relationships. However, there are several practical applications to these ratios. Let's take a simple example. Let's say you want to calculate the height of a building or a tree. One way you could possibly do this is to take a tape measure, climb the tree, and measure how tall it is. A less daft of a person would try to use the power of observational mathematics to do the same. What do we know about the environment? We can position ourselves at a point P in the world, and we can look up at the tree and measure the angle at which we need to tilt in order to observe the tree from our position on the ground. Let's call this angle theta. We can also walk over to the tree and measure the distance of the tree from our initial position. What we have here is a rudimentary right-angle triangle, where we've determined one of the angles and the length of the adjacent side. The information we're lacking is the length of the hypotenuse, which is quite hard to determine in our case using conventional means, and the length of the opposite side, or the height of the tree, the answer to which we're looking for. All we need to do is leverage one of the trigonometric functions and substitute the values. The tangent function comes to mind. Tan of the angle theta is equal to the opposite side over the adjacent side. Let's put a couple of concrete values here. Say the distance to the tree is 60 meters and the angle we are observing it at is 60 degrees. If we rearrange the equation, we can easily find the height of the tree if only we knew the tan of the angle of 60. Fortunately, I seem to possess the values of the tan function for a few key angles and they're tabulated here. That's handy. Tan of 60 degrees is root of 3 and root of 3 multiplied by 60 is approximately 104 meters. That's a tall tree. It was quite convenient that we had the tan conversion table. But how did we arrive at those values? Tan of theta is said to be a continuous function over the angle theta. A function in mathematics, or in programming for that matter, is a relationship where you can plug in or substitute any value for the parameter that it operates over, and you get an output in each case. Let's try to find the values of the sine function. For this, we need to simplify the triangle further. Any unknowns we can eliminate, the better. To do this, we turn to circles, unit circles.